Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
This is week 3, part 1 of Deep Learning and Generative AI. In this video, we introduce convolutional neural networks and explain why they are essential for image data. We're going to unpack exactly what they are and, maybe more importantly, why they are so absolutely critical when we're working with images. Okay, so first things first. Before we can really appreciate the genius of CNNs, we have to understand why our trusty old multilayer perceptrons, well, why they completely fail when it comes to images. You've seen how MLPs are great for nice, clean, structured data. But with images, they just fall apart. And the reason for this is a fundamental problem I like to call spatial blindness. Just take a look at this. It really hits the point home. On the left, we have a perfectly normal picture of a coastline. Everything's where it should be. But on the right, I've taken the exact same pixels and just thrown them into a blender, completely shuffling them. Now here's the wild part. To a standard MLP, these two images are basically the same thing. It sees the same colors, the same brightness levels, but it has absolutely no idea that the pixels on the left form a coherent scene and the ones on the right are just noise. It has no concept of neighboring pixels. So why does this happen? Well, it's because of what we're forced to do to an image just to feed it into an MLP. We have to flatten it, turn that beautiful 2D grid of pixels into one long, boring vector. And look what happens when we do that. Two pixels that were right next to each other vertically suddenly end up hundreds, maybe thousands of spots apart in that vector. All that crucial spatial information is just gone. The network then has to waste an enormous amount of effort just trying to relearn that these two far-apart numbers were originally neighbors. It's a hugely inefficient mess. And if that conceptual problem wasn't bad enough, it leads to an even bigger, more practical disaster. I'm talking about a catastrophic scaling problem, what we call the parameter explosion. Okay, let's put some numbers to this because it's pretty staggering. Let's say we have a totally reasonable, not even that high res, 1 megapixel image. That's 1,000,000 pixels, right? Now, if we want to fully connect every single one of those pixels to our first hidden layer, let's say it has 1,000 neurons. What's the math on that? Well, it's 1,000,000 inputs times 1,000 neurons. And that gives us 1 billion parameters. Just think about that, 1 billion. And that's just for the first layer of the network. We haven't even gone deep yet. A model like this is just computationally infeasible. You need about 4 gigabytes of memory just for those weights, and it would overfit on anything but an infinite dataset. So the takeaway is clear. The fully connected approach simply does not scale. So we're stuck, right? MLPs are out. What do we do? Well, the answer isn't just to make our MLPs smaller. The answer is to completely rethink the architecture from the ground up. We need to build a model that has better starting assumptions about the world, what we call a stronger inductive bias. We need a model that knows it's looking at an image. And that is exactly what a convolutional neural network is designed to do. CNNs are built on 3 incredibly powerful and, frankly, common sense ideas. These are the built-in assumptions that make them so good at vision. First, locality, the idea that a pixel's meaning comes from its immediate neighborhood. Second, what we call translation equivariance. Basically, a cat is a cat, whether it's in the top corner or the bottom corner of the image. And third, compositionality, the idea that we build up complex things, like a face, from simpler parts, like eyes, noses, and edges. By baking these ideas right into the architecture, we make the network's job so much easier. All right, let's break these down. First up, locality. This is a simple but brilliant constraint. Instead of every neuron looking at the entire image at once, we're going to force it to only look at a small local patch. Look at the difference here. On the left, that's the MLP's wiring diagram, a total mess, everything connected to everything. But on the right, that's the CNN. See how clean it is? Each neuron in the next layer is only connected to a tiny window of the input. We call this window its receptive field. And this isn't some random idea we came up with. It's directly inspired by how our own visual cortex works, based on the Nobel-winning research of Hubel and Wiesel. Just by doing this, we slash the number of connections and start to solve that parameter explosion problem. But just looking locally isn't the whole story. The next big idea, and maybe the most powerful one, is weight sharing. Think about it. If you have a little detector that's really good at finding, say, a vertical edge, wouldn't you want to use that same detector all over the image? Of course you would. An edge is an edge no matter where it appears. And the way we implement this is with something called a kernel or a filter. It's just a small grid of weights, like a 3x3 grid.
And we take this one filter and we slide it or convolve it across the entire image, applying it at every single position. The key is that the weights in that filter don't change. They are shared. And the result? It's just mind-blowing. Remember our 1 billion parameter problem? With a 3x3 kernel, that problem becomes 9. 9 learnable parameters, plus a bias. That's it. From a billion to 9. This is the magic trick that makes modern computer vision computationally possible. So what are these little filters actually learning to do? Well, they become feature detectors. The first layers of the network learn to spot really basic stuff, simple edges, corners, blobs of color. Then the next layer takes those simple patterns as its input and learns to combine them into slightly more complex things, like maybe an eye or a nose or the texture of fur. And you just keep stacking these layers. The deeper you go, the more abstract and complex the features get, until a final layer can look at a combination of eye and nose and fur detectors and say, hey, that's a face. It's a beautiful compositional hierarchy. Now, when you combine these two ideas, looking locally and sharing weights, you get this amazing emergent property called translation equivariance. It sounds complicated, but the idea is simple. If you move an object in the input image, the activation in the output feature map also moves by the same amount. The network doesn't just tell you if a feature is there, it also tells you where it is. This is why a CNN can find an object no matter where it is in the frame. It's a huge deal for building robust models.
All right, so let's pull all of this together and summarize why this architectural shift was so incredibly fundamental before we look at what's coming up next. So it all boils down to 3 major wins for CNNs. First, they have the right inductive bias for images. They bake in assumptions about locality and spatial structure. Second, this leads to massive parameter efficiency. We went from billions of parameters to just a handful, letting us build really deep networks. And finally, that translates into incredible data efficiency. Since a single filter learns a feature that can be used everywhere, the model learns way faster and from less data. This wasn't just an improvement on the MLP, it was a completely new way of thinking.
Okay, that's the theory. That's the why. But what do these things actually look like when we build them? How do we take these clever ideas and stack them up into a real-world model that can classify millions of images?
Well, that's exactly what we're going to cover in part 2. We'll walk through the Hall of Fame of CNN architectures. We'll start with the granddaddy of them all, LeCun's LeNet. Then we'll look at AlexNet, the network that really kicked off the deep learning revolution back in 2012. And we'll finish up by looking at more modern, deep architectures like ResNet. It's going to be a great session. I will see you then.